Okay, we'll make a start. So I want to mention a few things about the assignment. So you are in your third week of practice in CFD. So I have the students who have come to the classes, I have seen them doing almost all tutorials up to 4. All of you seem to have done 1, 2, and 3, and some of you have completed 4 as well. So in the assignment, what you will have to do is the first part is very similar to your tutorials 1, 2, and 3, and the second part, for the second part, you have to make a T-joint first, and then simulate it for both laminar and turbulent flow. You can use air or water as the fluid, or you can select a similar fluid, but make sure that the fluid is Newtonian. I wouldn't recommend you to do any non-Newtonian fluids. So if you want to do non-Newtonian fluids, you had to use CFX, not Fluent. So if you have any questions, ask me, email me. You can do it in pairs. You register yourselves on Blackboard for your pairs. Ideally it has to be a new pair. So if you have any problems, email me. Okay, we'll start from last week. So we looked at the equations, governing equations for computational fluid dynamics, or governing equations basically for fluid flow, really. And we looked at the continuity equation. So it can be written in 2 forms. This is the longer version of the equation, where you have the time derivative and the spatial derivative. So the spatial derivative can be written as a function of, this is called nabla. This term is called nabla, or that is the partial derivative, dava by dava x plus dava by dava y plus dava by dava z is the derivative, and you derive that. Then you differentiate the velocity vector u. Right? So that's the continuity equation, and that's the rate of change of density in time. So that's the time differential, that's the spatial differential. And then for steady flow, you know so there is no rate of change of density in time. Therefore, you can equate that to 0. So for your steady flow, only your spatial derivative is equal to 0. And for incompressible flow, your rho doesn't change. So you can take it out. It's a constant. Here it doesn't change in time. Here it doesn't. It stays a constant. Okay? So therefore, you can take that out as well. For incompressible flow, your spatial derivative of the velocity vector becomes the continuity equation. Okay, and then we looked at how the Navier-Stokes equations are derived from the continuity, momentum, and energy equations. So for incompressible flow, again, in the Navier-Stokes equation, you take the rho term out of the equation, or make rho constant, and then you remember you have a nu or mu term, which is the viscosity term in the Navier-Stokes equation. So as I mentioned that I mentioned earlier that this is for a Newtonian fluid. if the fluid is not non-Newtonian, your mu changes with the stress tensor. So that's additional equation. So we are not looking at it at this stage. Okay. So when we look at the viscous term, if we say the fluid is non-viscous, you take the mu away as well. So for non-viscous fluids, we can take the mu away as well. Therefore, your Navier-Stokes equation will reduce to the this is your time derivative, that is your spatial derivative, that is the body force, and that is the spatial pressure difference. Okay, so you don't have any viscous terms in that. So that's called, those are called Euler equations. So Euler equations are reduced form of the Navier-Stokes equations. And inviscid flow is theoretical only, but it's very useful for you to analyze fluids. So now these are mathematical equations. So the good thing about mathematical equations is that you can draw things in maths if you know, for example, x squared plus y squared is equal to r squared, means a circle. Yes. So likewise, you can define paths, etc. Paths, velocities, acceleration, everything you can visualize if you know your maths. If you can describe in a mathematical form. Okay. So, for example, air and water are, well, they are viscous, but you can get a good approximation of the flow by equating them to a non-viscous flow. You can get the flow pattern. Okay. So adding viscosity will give you an extra dimension to the description of the flow. Okay, so that's the end of the description of the mathematical equations. Now we want to look at how we can solve these equations in a discretized form. What is meant by a discretized form is, okay, once you have written those mathematical equations, what you ideally you want to use your mathematics knowledge to solve them, but these are large equations, and it's a large set of equations, partial differential equations, not even simultaneous equations. They are partial differential equations, meaning you need a computer to solve these equations. So that is what is done in computational fluid dynamics as well as in finite element analysis. So what we do and discretization is that we write the equations in a discretized form. You will realize what this, okay, we have done this for mathematics in your second year perhaps, or in the first year, but we will go through some of the concepts briefly here too. So the difference in a discretized form and in a mathematical form is that in a discretized form you solve the equation for a small element or a small domain, but when you write the equations in the mathematical form, you write the mathematical equation for the full domain. So what you mean by discretizing that you chop the domain into small elements and try to solve the equations for those elements and take the solution for that element to the next element and solve the equations again, get a solution, and you take that solution to the next element. So that's called an iterative process. So computers cannot solve differential equations if they are not written in discretized form. So you can't just write your algebraic equations, your mathematical equations, unless you make them to algebraic equations. Algebraic equations means they are numeric. You can write numbers and get numbers as answers. Okay, algebraic means you write numbers, input numbers, and take answers as numbers. Okay, there are few discretization schemes. One is the finite difference method, and the other one is what you call the finite volume method. Finite difference method is 1D, meaning if you take a line, you chop it or discretize it into small elements, and then you carry on a calculation starting from one end and advancing to the other end, one by one part. So that's a finite difference method. So you have done this. I'm sure you have done Runge-Kutta method, etc. At some level in maths. And then finite volume method. In finite volume method, what you have is this is used for solids basically. So you discretize your domain or cut and chop your domain into a finite number of volumes, and then you start with one volume, solve the equation to that volume, take the answer from that volume, go to the next volume, solve the equations, get the answer, go to the next volume, etc. Okay. And then you have the finite element method. So finite volume method is used in CFD, and finite element method is used in for solids basically. So finite volume method is used for fluids, and finite element method is used for solids. And you use the finite volume method in your FEA, finite element analysis calculation, FEA calculation. Okay. And there are other methods which are not less common, which are called spectral methods, boundary element methods, and particle methods. So now these are used in special circumstances, etc. So particle methods are used sometimes in CFD. Those are used for combustion, etc. So you are not going into that detail in this subject at this level. Okay. So we will not be learning about this any further. So finite, so you can use your equations to solve anything anywhere at any space, but in engineering what you have to do is you need to make your problem, you have to make your problem bound. That means you need to define your boundaries correct. You have to have boundaries, and you have to enclose your space where you do the calculations. For example, if you have a pipe flow, your boundaries are the walls and the inlet and the outlet. So you're not worried about outside the inlet or outside the outlet, outside the walls. You're not worried about it. You have a specific volume which is within the boundary. So all the problems that you are going to solve in CFD as well as in FEA, you need to make a boundary. The problem should be bound. So finite difference method is based on Taylor series expansion. So we will look at how it can be applied. This finite difference method is also used in your it is partially used in your finite volume analysis. So when you did your tutorial problems, you must have entered somewhere what is the finite difference method that you had to use. So it asks you at some point when you do the simulation, you need to enter the finite difference method. You must have said simple. To use a finite difference method, you need to have a structured grid. A structured grid, we talked about structured grid. Remember, in a structured grid, for example, if you have a cube, you have the same number of grid cells in the x direction and y direction and z direction. In the sense, it resembles a hexahedron, every element and the full domain as well. Okay. I will talk about what you call the Taylor series. Taylor series, if you have a function x, fx, and if you increase x by delta x, you can write the Taylor series expansion as fx plus delta x is equal to fx plus dabba f by dabba x delta x plus dabba squared f by dabba x squared times delta x squared over factorial 2 and so on. Okay, this is called factorial. And this is a quite a, if you go beyond here, these terms become higher order terms. And when these become higher order terms, now this delta x is a tiny element, isn't it? X is the large one, delta x is a tiny element. And third or fourth derivative, in power of a tiny element is a tiny element. Okay. So in which case you will be neglecting higher order terms. Now remember, this one is, for example, if your delta x is 0.1, this will become 0.01 divided by 2. This will become 0.001 divided by 3. The next one will become 0.0004 divided by, this is not divided by 3, this is divided by 6. The next one will be divided by 0.0001 divided by factorial 4. So that is 24. So likewise, that will become smaller and smaller and smaller. So when you compare it to the size of these elements, you can neglect them. Yeah. So suppose you have a function fx like that, and if you take only the first element, your x plus delta x will be something like that. Okay. That will be your difference between the actual and the approximation. Okay. So that's the first order approximation. Okay. And if you go second order, it will be smaller than that. If you go third order, it will be further smaller than that. Okay, so the higher the order, the more accurate is the solution. So see, so your second order error is that much, your first order error is that much. So the second order error is like, it's half the first order error. And if you go third order, you will become, it is quite close to your solution. Okay, for the Taylor series expansion. Now this is an example again for fx. Your function is sine 2x. So that's your so these are first order, second order and third order solutions, where you have reduced your error significantly. And we will look at now that's an example. The sine 2x is sine 2 pi x is an example, and this is what we need to discretize. Yes, so we need to use finite difference method to solve the Navier-Stokes equation. And we will see how we can approximate the partial derivatives here using finite difference, using the Taylor series expansion. So you have your time derivative of velocity, you have your special derivatives of velocity, you have the body force, you have the pressure term, and you have the viscous term in the Navier-Stokes equation. So this is what is done in your codes, in your CFD codes. But we are not going to do this in a book. We will use the CFD code for that. But we will do some examples which resembles to the method closely. So in the Navier-Stokes equation, you use the W by W x term using a finite difference method. Okay. So how you write that is you have your ui plus 1j, that is uij first is the first term, is where you start, and ui plus 1j is your next term. Okay. And that can be written as a W by W x ij plus delta x. That's your finite. That's the grid size. Delta x is that length. Okay. And W squared u over W x squared, delta x squared over factorial 2, and so on. This is the Taylor series expansion. Okay. And when you rearrange the this equation, meaning you take this to here, W by W x ij. So that is you're writing an equation for this one. So you can rearrange it as follow like this. You take a I plus 1j to the right hand side. You take this one to the left hand side, and then now that is called the finite difference representation. And if you neglect these ones, that will be your truncation error. Okay. So that is your finite difference approximation. That will be your finite difference approximation, and that will be your truncation error in the first order. Okay. If you take it to the second order, your finite difference approximation is that, and that will be your error. Okay. So here, this is the first order forward difference error. this is, oops, that's your first order forward difference approximation. Now that is your error, that is your approximation. And this is first order forward difference. Forward difference means you go forward, you go I plus 1. Okay? If you went I minus 1, that will be backward difference. And that is your backward difference approximation. Okay. And again, that would be your truncation error, and that would be your finite difference representation. So that's your that would be your first order backward difference approximation. Error. This would be your first order backward difference approximation. Okay. And then you can go further. Then you can have a what you call a second order central difference approximation, in which your truncation error is starting from the third order terms. So you consider the second order terms into the finite difference representation. So that is your, so in this case your truncation error is smaller than in this one. Okay. So this is second order central difference. So in the central difference scheme, you have your I plus j term as well as your I minus j term. So this is the finite difference approximation, and this is the second order central difference scheme. That's a full scheme. Yeah. So these are the different schemes that we talked about. This is our first order forward difference scheme with respect to x. This is our first order backward difference scheme with respect to x. That's your second order central difference scheme. This is your second order second difference scheme with respect to x. And you can have the same in the y direction. So that's your forward. That's your forward. Now you start with that central cell anyway, central node, and that you go back in the y direction. That's your central difference. That's your second difference with respect to y. That is a fourth order central difference scheme, where you have for one node you take 4 other nodes into your calculation in one direction. So you could see that in your first order calculation, you only took one node. You only took one node in your first order calculations. In the central difference scheme, you took 2 nodes, whereas the second order second difference scheme, you took 3 nodes. Now in here, you take 5 nodes or 4 other nodes into your calculation when you go fourth order. But the good thing about this is when you go higher in the order, your approximation is more accurate, but on the other hand, you do more number of calculations, meaning because you do more number of calculations per each cell, and you need to do all the calculations for every cell. and your computational time will increase. When the higher the order, the larger the time that is taken for the calculation. Okay? The higher the order, the larger the time that is taken for the calculation. But the good thing is you need a smaller number of grid cells. So this is the trade-off. Okay? Remember, if your differencing scheme is really complex, if you have taken, if you have a higher order differencing scheme, your grid can be coarse. But if your grid is really fine, that means you have a large number of nodes in the grid, you can get away with by having a lower order differencing scheme. Yes? With the geometry, it depends on where your gradients are higher and where your gradients are lower. For example, now we are talking about the T-junction that you have to do in your assignment. Okay, it's a T like that. So at these corners, where the base meets the pipe, you need to have a really high resolution here, grid nodes, good grid resolution, for you to solve those high gradients. Okay, so it depends on the geometry when you have high gradients. Does it make sense? Far away. Ask again. Did it answer your question?
So just with the finite picture, the forward, right, and the backward.
Yeah.
Does it depend on the geometry of the actual element itself?
Okay. Now, if it is a simple geometry, you can have hexahedrals, yes? Hexels. So it goes along with the geometry itself. But if your geometry is complex, you may not be able to have hexes. Then you will have to have tets. Okay? So that means it may be slightly less accurate, isn't it? So in that case, what you have to do is you have to have a really fine mesh to resolve those. If your geometry is complex, you have to have a fine mesh, because you can't have a regular mesh for a complex geometry. Okay? Right. Good question. And so in Navier-Stokes equations, when you write the Navier-Stokes equation in the CFD code, you have a partial differential. You have a partial differential equation for all the partial derivatives, and they are replaced by different finite difference equations or finite different quotients. Okay, so you have to write the full equation with the finite different approximation. Okay, you can't have equations themselves, so you have to discretize it to finite difference approximations. So this is a full equation using, so this is the Navier-Stokes equation, and the Navier-Stokes equation written in the finite difference form is that. Okay, so you have your W by W x term, and the spatial derivative term here, and your force and your pressure term and your viscous term here. So everything is written in a finite difference form. Okay. Now that is the furthest we go with this. So I hope you get the feeling, I hope you understand what is meant by a finite difference scheme now. So we will look at some elementary examples. Now remember, one of these will be in your exam. So understand it properly. Okay. Okay. Now this is what you call the one-dimensional linear convection equation. So W by W t plus CW by W x is equal to 0. Now that is a time derivative. That is a spatial derivative with a constant c. Yeah. And this is a linear problem. So there are two partial derivatives here, W t and W x. So we need to discretize it with t with respect to t and with respect to x, with respect to time and with respect to space. So we'll take the spatial integral form as I, or the index as I. So xi means the first node, xi plus 1 means the second one, and so on. And let n be the index of the grid in t, in time. Yeah? So if you write a forward differencing scheme for the time, you can say W over W t is equal to ui n plus 1 minus ui n over delta t. That's your time derivative, time step. Okay, that's your time step. So that means it's not a second, it may be a part of a second. Yeah, time step. So if you use a backward differentiating scheme in space, W by W x can be approximated to uin minus uin I minus 1. Now remember, watch, observe that your n hasn't changed here. That means that's in the same time, but a different node. Now in here, it's the same node. This is a different time. Yeah. So that's the forward differencing in time, backward differencing in space. Yeah. So your discretized form of the equation can be written as, so your W by W t is that's your approximation. W by W x is that's your approximation. Okay, and that will be equal to 0. So that is your discretization scheme. And n and n plus 1 are two consecutive time steps, while I minus 1 and I are two neighboring spatial points or grid nodes. Okay? And okay, we got 10 more minutes. I think we can finish this one. Good. And another example is the diffusion equation, the famous diffusion equation which you used, which you have seen in your first year, second year heat transfer. So we will use a forward difference in time with index n and central difference in space with index I. Okay. So remember, time is first order. This one, it has the equation itself is in the second order, right? Remember, you have two here. So the discretization form for time can be written in this form. So that's your second order equation. Okay, that's your v. That's your u I plus 1 n ui n. Now there you see your time doesn't change. Okay, if you solve for uin plus 1, now that is uin plus 1, you have to take the other terms onto the other side of the equation. So that's your in plus 1. Now we are still doing it for the time derivative. Yeah. And then we need to write an equation for we need to write a finite difference equation for the spatial derivative. Yes. Oops. Oh, sorry. Now that's your time derivative. That's your spatial derivative. That bit is your time derivative. That bit is your spatial derivative. Okay. Now that is your time derivative. This part is your full spatial derivative. That's second order. So look at this in comparison to that one. Now in here you have only delta t and delta x, no squared terms because the equation doesn't have squared terms. And if you go here, you see that your delta x is in the squared form because that's the second order equation. Okay. Right. And we'll look at another example which is called the Burger's equation. Now this one has a time derivative in the first order. You have a spatial derivative in the first order as well as another spatial derivative in the second order. Yes. So the approximation is for the time time derivative. We approximate to uin plus 1 minus uin over delta t, and for the second term u w by w x you have ui plus 1 n minus uin. Now that's in space, right? Because that is, so you have to use I plus 1 and I for the space delta x, and that's in the first order. And now for the viscous term or nu W squared u over W x squared, you have that one nu times uin plus 1 minus 2 uin plus uin minus un I minus 1. This one is un I plus 1. Now that is again in the space. Now these are in the space, not in time, okay? Because I changes in space. Yeah? And you have used delta x squared here. That is because you have a delta x squared in here. So if you write the full equation now, you can write it in this form. Okay? That's your w over w t. That's your uw over w x. That's your new w squared over w x squared. So that's the full differential equation, the finite difference equation. Okay. And then you can, that's your equation, and then you take your uin plus 1 to the left hand side so that you can integrate. Okay. And so the finite difference method is the oldest and easiest to apply, and it relies on a structured mesh. Okay, so you have to have a structured mesh for the finite difference scheme to apply. And but if you have a structured grid, you can use this method for fairly accurate calculations. And then we have what you call the finite volume method. So in finite volume method, you do a volume integral rather than a difference integral. So you do the integral for the whole volume itself. Okay. That is what is used in CFD, and the good thing about finite volume method is you can use it for an unstructured grid. Okay. So finite difference method, for finite difference method, you need to have a structured grid, whereas for finite volume method, you can have an unstructured grid. An unstructured grid means if you take a 2D space here, x and y, so you can have 10 grid nodes from in this direction, and you can have 6 grid nodes in that direction. You can have 7 grid nodes in this direction, and you can have 11 grid nodes in this direction, and you can have triangles in between. So that's an unstructured grid. Okay. And finite volume method is mostly used in engineering solutions because of the question that you asked. When you have complex geometry, you may not be able to use a finite volume method. You may not be able to use a finite difference method. You will have to use a finite volume method or an unstructured grid. You can't have a structured grid for a complex geometry. For example here, so this is a finite volume method used in here for a pipe problem. So your integral equations are transformed into a set of algebraic equations, and we use them numerically using a computer. And for each finite volume, we solve the equations of mass, momentum, and energy. Mass, momentum, and energy. So it is at this level, but when you have combustion, etc., you will, when you have combustion or reaction, you will use the chemical equation as well. You will have the chemical equations as well, but that's out of scope at this level. Okay, if you are doing a project that involves chemistry as well, come and talk to me when you do it. So your ANSYS is based on finite volume method. Okay, we'll quickly go through what is meant by an implicit scheme or an explicit scheme. In an implicit scheme, you have one difference equation has one unknown, and you solve for the rest. Okay. In an implicit scheme, you don't have just one unknown. You have many. One tangle to another. So you have to solve everything together to get an answer. Okay. So in an explicit scheme, explicit schemes are numerically less demanding, and it takes less time. When you have an implicit scheme, when you have an implicit scheme, it will take more time. It takes more time to solve. Okay. Then what? For example, this is an iterative solver. So for if you have these simultaneous equations involving x, y, and z, what you do is you write an equation for x in terms of y and z. You write an equation for y in terms of x and z. You write an equation for z in terms of x and y, and then you can do a difference scheme and solve for x, y, and z. So this is another way of doing it. That's what your calculator does actually. And then you have what you call relaxation factors. So relaxation factors are the answers that you use, that you have an approximate answer, and your approximate answer for the next step is a is the answer for the previous step plus a predicted value minus your old value times what you call a relaxation factor. So you must have used this method at some point in your maths. So if your u is equal to 1, there is no relaxation. If your u is greater than 1, you have over relaxation. If your u is less than 1, you call it under relaxation. So this is used to expedite calculations. So you use a relaxation factor to expedite calculations. So you can reach your answer quicker when you use a relaxation factor. Okay. Thank you for listening. That's your third lecture done. And if you have any questions, please email me or ask me in the classes.